So I'm going to run through the solutions to the related rates ZipGrade practice quiz that we had recently. A conical paper cup is 30 centimeters tall with a radius of 10 centimeters. The cup is being filled with water at a rate of 9 pi over 4 centimeters cubed per second. How fast is the water level rising when the water level is 5 centimeters? And of course, we've got some choices here for our answers. So let's start by drawing a picture like we usually do. So I'm going to draw the container, which is the paper cup, and it's a cone, and it happens to have a radius of 10 and a height of 30. So this height is 30. That's constant because the paper cup is not changing. And this distance here is 10 centimeters. And that is the container for some water that's being poured in. So we've got water going into this thing, right? And the cup is filling up with water. Now, the shape that the water makes is also a cone, and it has the same proportions. In particular, what's going to come into play here is that the relationship between the radius and the height is 10 centimeters to 30 centimeters. In other words, the height is 3 times the radius, and that's going to become important for us later. Let's list the rest of the information that we have here. Water is coming in at a rate of 9 pi over 4 centimeters cubed per second. That's this guy right here. That is a rate for the volume. And remember, the rates are our derivatives. So this is dV over dt, and that's going to be 9 pi over 4. Hopefully that looks like 9 pi over 4. And that's cm cubed per second. And then we are interested in how fast the water level is rising. Well, I don't have any variables on this picture yet, other than the fact that I mentioned a volume. Remember, the volume is kind of like the amount of water that's in here. What we also have is the height of the water, and the water itself has a radius. I'm going to draw that with a little green measurement. So the cone of water has a height and a radius, and both of those are changing, as well as the volume. And now that I've labeled those variables, I can make use of this information. First of all, how fast is the water level rising? When we say that, we mean dH dt, and we don't know what that is. We want to figure it out. So that's what I'm trying to find. And then we're told that we're interested in that measurement when the water level is 5 centimeters. So they're telling me that H is 5 cm at that time. Okay, now what is the formula that relates the volume, the radius, and the height of a cone? Well, you go back to your geometry class and you remember that V equals 1/3 pi r squared h. And I notice that there's but there's several variables in this equation. And in particular, I don't have a lot of information about r. But what I do happen to know is that there is a relationship between h and r. And so I have a couple of choices. I can either replace h in this formula and just work with r, or I can replace the r squared by solving my white equation down here for r. And since I'm kind of lazy and I don't feel like solving this equation right now, I'm just going to replace h with 3r. So I'm going to put 3r in here. And when I do that, I end up with a new equation. The 1/3 times the 3 cancel out. I end up with pi r cubed. And from this equation, I can go ahead and do the derivative, which is dV over dt equals 3 pi r squared dr over dt. Now, this is good news. I've got my my derivative written out here. All I need to do is plug in numbers for dV dt, r, and dr dt. Let's see, what's going on here? Ooh, I made a huge mistake. I was supposed to find dH dt, and so the choice up here that I made for plugging in 3r in for h. While it did eliminate my variables and made the derivative easy, it is a problem because I don't have any h's in my equation anymore, and how can I solve for dH dt if I don't have that? Now, there is a way I can recover from this, but it's going to take me more time to do that than it is to just start over. And so by starting over, I mean I'm going back to the decision I made to put the 3r in, and instead I'm going to substitute r equals h over 3, right, from this equation, right? If I solve for r, I get that. And I'll put that in right here, and I'm going to write a new equation. I'll do this all in blue then. Am I going to be able to fit this in? I don't think I'm going to be able to fit it. Let's move to the next slide, and we'll do that. So I cleaned up my mess a little bit here. And remember that our formula was 1/3 pi r squared h. And I mentioned that I can solve this equation right here for r, and I can write that r equals h over 3. We really want this to be in terms of h. It'll be a more direct way to get to what I'm trying to solve, which is dH dt. So what we do is we rewrite this equation. V equals 1/3 pi. Instead of r squared, I'm going to substitute h over 3 for r. That becomes h squared over 9. When you do h over 3 squared, you get h squared over 9. And then there's still that other h. And so this formula becomes, I'm going to combine the pi with a fraction, and it becomes pi over 27 h cubed. This is the formula that I'll take the derivative of. So dv over dt equals, when I bring the 3 down, that's going to reduce this fraction to pi over 9 h squared dH dt. And now I can substitute my values in. So I know that dv over dt is 9 pi over 4. And I know that h is 5. So we'll plug in 9 pi over 4 equals pi over 9. And then because h is 5, I'm going to put 25 right there, because h squared would be 25. And then I'm going to solve for dH dt. And when I do that, essentially I just have to divide by 25 pi over 9. Pi is going to cancel, some other stuff's going to happen, and the calculation ends up being dH over dt is approximately, actually it's going to equal exactly. I want to make it match those fractions. So let's go ahead and write this thing in, and we'll just reduce it. I'm running out of space though. So I'm going to have 81 over 100 when I do that. And yes, oh, but don't forget this is centimeters per second, because we're asking for how fast this thing is rising. And that's good news, because I do have that as a choice, right? 81 pi over 100 is what you get when you solve this thing, and that is choice D right here. Whew! All right, so I salvaged a disaster there, but it's good for you to know that if you don't attack a problem in the right way, you may end up with an equation that doesn't include the variables that you are looking for. So we made it. Let me go ahead and move on to the second problem here, and then we'll wrap this video up. Water slowly evaporates from a circular-shaped puddle. The radius of the puddle decreases. That's a good word there. I need to highlight that thing. The radius decreases at a rate of 4 inches per hour. Assuming the puddle retains its circular shape, at what rate is the area of the puddle changing when the radius is 5 centimeters? So essentially what they're saying is, hey, we've got this puddle, and it's evaporating, but it's evaporating in such a way that the circle is just shrinking. Now, I don't know if that's the way water actually evaporates, but in this story it is. And so the area of this circle is changing, right? This is the area inside here with all the water. And the radius is also changing. Both are getting smaller. And we're interested in at what rate the area is changing. Okay, so we're trying to find dA over dt. That's the thing we're trying to find. We are given some information. We know that at the time in question, r is 5 inches. And we know that the rate at which the radius decreases is negative 4 inches per hour. That's dr over dt. I'm making that negative because this thing is decreasing. And rates, remember, they do have direction. Okay, so I have variable a, I have variable r. We're talking about a circle. I think you'll remember that the equation that relates the area of a circle to the radius is a equals pi r squared. That's a famous formula. Then we'll go ahead and do the derivative implicitly here with respect to time, and I end up with dA over dt equals 2 pi r, and then don't forget that chain rule, dr over dt. And I'm going to plug in negative 4 for the dr dt, and I'm going to plug in 5 for the radius, and I end up with dA over dt equals 2 times pi times 5 times, so what is this, negative 40 pi, and that is inches squared per hour. Ooh, good. So I do have that equation, right? Or that, oops, what am I doing here? I do have that answer. So I came up with negative 40 pi inches squared per hour, and that looks like letter A right there. So we're in good shape. Okay. This problem was a little easier to attack than the last problem. The reason those cone problems are a challenge is because you have to make that connection between the radius and the height. The container will show you what the proportion is, and then you work from there. So hopefully this helped at least explain, if you had issues with these problems, how to get the right answers. And especially on that number 1, I sort of demonstrated how if you go down the wrong path, you could end up with an equation that doesn't help you. The other thing I want to show you in this video is when that happens, when you make a mistake or you head down the wrong path, you don't panic. You go back to a place where things were going well, and then you just redo the problem, right? You redo your solutions. So that's what I did. Rather than, just delete the video and start over, I decided to show you that, you can recover from those mistakes. Good luck with your preparation, and we'll do a real quiz here pretty soon. Let me know if you need anything. Take care.